If you've ever taken a road trip, you've probably noticed those enormous steel structures stretching across the landscape, carrying the power lines that deliver electricity to our homes. They're everywhere, crossing mountains, valleys, rivers, and cities. But if you look a little closer, you'll notice something interesting. They don't all look the same. Some are wide and extremely robust. Others are much slimmer and supported by long steel guy wires anchored to the ground. And then there are towers that look like giant metal puzzles. So, why do transmission towers come in so many different shapes? Today, we're going to explore the engineering behind these impressive structures and discover that every beam, every angle, and every curve is the result of careful mathematics, physics, and decades of engineering optimization. The main purpose of a transmission tower. To understand why transmission towers vary in design, we first need to understand what they actually do. Their job isn't simply to hold electrical wires. Transmission lines carry electricity at extremely high voltages, often 230,000, 345,000, 500,000 volts, or even higher. At these voltages, electricity naturally seeks the shortest path to the ground. That's why a transmission tower must keep energized conductors safely separated from the ground, nearby objects, and from each other. Its design is the result of balancing two major engineering requirements: electrical safety, mechanical strength. The tower must support several tons of cables while resisting wind, rain, ice, temperature changes, and decades of continuous operation. Suspension towers. The most common type found along long, straight transmission corridors is the suspension tower. As the name suggests, its primary function is simply to suspend the conductors. On these towers, the insulator strings, the components that resemble stacks of ceramic discs, hang vertically beneath the crossarms. The tower mainly supports the weight of the conductor's wind loads acting sideways. Since it doesn't need to resist significant pulling forces along the direction of the line, it can be lighter, simpler, and less expensive. That's why you'll often see dozens of nearly identical suspension towers lined up along straight stretches of transmission lines. Anchor, strain, towers. Everything changes when the transmission line needs to change direction or terminate. In these locations, engineers use anchor towers, also known as strain towers or angle towers. Unlike suspension towers, where the conductors simply pass through, the conductors are firmly attached to the structure. You'll often notice that the insulator strings on these towers are mounted horizontally, aligned with the conductors. This happens because the tower must resist enormous mechanical tension created by the cables pulling toward the bend. These towers are significantly heavier. They feature wider foundations, larger steel members, stronger structural bracing. Their robust construction ensures that the transmission line remains stable even if a conductor breaks on one side, preventing the domino effect. Anchor towers serve another critical purpose. Imagine a transmission line hundreds of miles long made entirely of lightweight suspension towers. If one tower collapsed, it could pull down the next tower, creating a catastrophic domino effect stretching for miles. To prevent this, engineers strategically place anchor towers every few kilometers. They act as structural barriers, stopping failures from propagating throughout the entire transmission system. This simple design choice dramatically improves grid reliability. Guide towers. One of the most visually distinctive designs is the guide tower. These towers often resemble an inverted V or Y, supported by steel cables called guy wires that extend outward and anchor into the ground. Guide towers are masterpieces of material efficiency. Because the guy wires absorb most of the wind and tension loads, the central steel structure can be much lighter. Their advantages include lower steel consumption, faster construction, lower installation costs. They're especially useful across wide, flat terrain where transporting massive steel structures would be expensive. The downside? Guide towers require a much larger footprint because the support cables need substantial space for safe anchoring. Self-supporting lattice towers. When available land is limited, such as near cities or in mountainous terrain, engineers typically choose self-supporting lattice towers. These are the classic steel towers most people recognize. Unlike guide towers, they stand entirely on their own, without external support cables. Their advantages include Smaller land requirements greater versatility, excellent structural stability, ability to reach exceptional heights. Although they require more steel than guide towers, they're often the best solution where land is expensive or terrain is challenging. They're also commonly used for crossing wide rivers, deep valleys, and highways. Choosing the right tower. Selecting the appropriate tower type involves much more than appearance. Engineers evaluate several factors, including soil conditions during construction, logistics, wind loads, environmental conditions, long-term maintenance. For example, rocky ground makes it easier to anchor guy wires. Soft or sandy soils may require massive reinforced concrete foundations, making self-supporting towers the better option. Fighting corrosion. Corrosion is another major design challenge. In coastal regions, salt carried by sea air accelerates steel deterioration. To combat this, transmission towers are typically protected using hot-dip galvanization, creating a zinc coating that shields the steel for decades. Every structural component, from steel angles to bolts, is designed to provide a service life of 50 years or more. Why are transmission towers full of holes? Have you ever wondered why transmission towers look like giant steel skeletons instead of solid columns? The answer is wind. A solid tower would behave like a massive wall, creating enormous wind resistance. That would require much larger foundations and far more steel. Instead, engineers use lattice structures that allow wind to pass through with minimal resistance. This dramatically reduces the forces acting on the tower. The same principle explains the design of famous structures like the Eiffel Tower. Their open framework allows them to remain both lightweight and incredibly strong. The future of transmission towers.